Okay, continuing on in part 3, example 5 says use transformations to sketch the following graphs. And the first graph they ask us to sketch is g of x is equal to x minus 1 to the third power. We know all about x minus 1. We know that we know all about x cubed. We know x cubed is our cubic function. We know that typically it looks like this, but we're transforming it, that minus 1, because it's on the inside, affects the graph horizontally, and we'll shift it to the right. So we're going to shift it right 1, and then we're going to draw in our nice little S shape. It looks something like that. They also want us to graph h of x is equal to x plus 5 quantity squared. That's our friend the parabola. So know that the graph is going to look like this. It is positive because the leading coefficient is a 1, so we know it's going to open up. In this case, again, it's been shifted horizontally. We're going to go left because we're doing the inside shift. We always do the opposite, so we'll go left 5. And it looks something like this. So we already know how to do that. That was all about chapter 3. Okay, well, in the box, it says crossing and touching at each x intersect. So if the multiplicity of the 0 is odd, so this is an odd multiplicity sitting over here, multiplicity, then the graph of f crosses. So there's a blank there. We're going to put in the word crosses the x-axis. Okay, let's backtrack now that we've got the crosses filled in. So what we're saying is if this 0 has an odd multiplicity, we know the graph is going to cross. So we know that it's going to do this and cross at that 0. What if the multiplicity is even? So this one is an even multiplicity. That's this 2 that we're talking about. Over here, we were talking about the 3, but this is an even multiplicity. So if the multiplicity of the 0 is even, then the graph is going to, I like the word bounce. So in that next spot, we're going to put in bounce the x-axis at R. So here the graph is bouncing at that 0. Over here, the graph is crossing, which we already knew. We just hadn't bothered to formally state it. Turning points. So turning point is when the graph changes direction. So the parabola is a perfect example of something that has a turning point. So it goes from decreasing to increasing. So this point right here, which we call the vertex in chapter 4, is a turning point. And turning points can help us graph the polynomial functions. So this graph has a turning point. This graph does not have a turning point. It is increasing all along its length, so it never changes direction. So a graph can have a turning point, but it doesn't have to have a turning point. So in the box, it says if f is a polynomial function of degree n, then f has at most n minus 1 turning points. What does that mean? So I'm going to go for this guy. If we were to expand this one out, it would have a degree of 2 because it's a quadratic. So that means in terms of turning points, at most, it can have that degree of 2, take away 1, and we would end up with 1 turning point. At most, it will have 1 turning point. What about this guy then? So this is a degree 3. So in terms of turning points, I'll do a TP for turning points. So we take that degree, take away 1, and end up with 2. So at most, it can have 2 turning points. It does not have to have 2 turning points or 1 turning point, but at most it will have 2. Now, eventually we'll graph some cubic functions that do have those turning points. So we'll end up with things that look like this is a cubic, and you'll see there's a turning point here and a turning point here. But our base function from our library of functions does not have a turning point too. At the very bottom of the page, it says if n is even, that was the degree, then it will have an odd number of turning points. And if the degree is odd, so if n is odd, there would be an even number of turning points. This is a point of fact. So, okay, I think we're ready to put all, oh, no, we're not. Sorry, I was jumping the gun. Next up, we'll talk about end behavior. Okay, what you're going to see are 4 different pictures, and we already know all 4 of these pictures. We're just going to finally formally state them. So the end behavior is basically what happens at the ends of the graph. So it tells me where the graph starts over on the left side, sorry, and where it ends over on the right side. It doesn't tell me anything about the middle of the graph. It only tells me what happens on the left side and what happens on the outside, on the right side. So it's the power function that's going to dictate this. So we're going to look at something called the power function. Okay, now we've already looked at two very specific power functions, the x squared as a power function and the x cubed as a power function. So let's pull those back in. So if we have an even degree, that would be our parabola. So think about x squared, right? We know that when the leading coefficient was positive, that x squared, so we're thinking about f of x is equal to ax squared. We know that when this was positive, that the graph started above the x-axis on the left side and ended above the x-axis on the right. So in terms of the end behavior, it did this. Started above, ended above. Okay, well, what if we made that a negative? So if we come in and make a less than 0, so what we're talking about is f of x is equal to, again, ax squared, where a is negative. Then we know that the graph is starting below and ending below. So that did a reflection for us. So for the power functions that are even degrees, if the leading coefficient is positive, starts above, ends above. If the leading coefficient is negative, it's going to start below and end below. Okay, what about an odd degree? This would be our x cubes. So think about those x cubes. Same exact conversation. We're going to talk about a being positive. Sorry, I need to get a little bit smaller. So if a is positive, so something like f of x is equal to ax cubed. Well, our cubic function started below, but it ended above, right? So it started below and ended above. Well, what happens if we make that a negative? Doesn't that do a reflection? It's going to reflect what we're saying here. So if your leading coefficient is negative, again, still looking at an odd power function, then it's going to start above and end below. Now, what happens is as we move up in terms of exponents and power functions, and x to the 4, because it's an even degree, will mimic these guys. And x to the 5th would mimic these guys. X to the 6th, x to the 7th, and so forth. So if you know the overall degree of your polynomial function, that's its power function, and you can tell me where it's going to start and where it's going to stop. So I think we're finally ready to analyze the graph of the function without the calculator. And I think I'll pick that up in the next part. That way it puts the two examples of actually analyzing together. So